Good day to you all, wherever you are, and welcome to the British Interplanetary Society's 22nd live stream evening lecture since the start of the first lockdown in March of last year. It's great to have so many of you here today, particularly at such, fairly short notice. For those who don't know me, I'm Alistair Scott, a past president of the Society, and now as chair of the events committee, I try to keep all our events and activities going. I won't waste time telling you all about the BIS and what it does and how great it is to be a member. I'm sure that most of you will already know. Anyway, I'll tell you a little bit more about our upcoming events after tonight's talk, if I have time, but I can say that we are planning to be back in the BIS for our talk on the 21st of October. So let's hope that we can all gather there this time. I think we'll be streaming them again live from there too, so that should help. Today we're again using Crowdcast for both the presentation and the Q&A, so most of you are already familiar with it. Please use the chat box for your networking and the questions box for your questions, and keep an eye on the questions box as you can vote up the questions that you want to go to the top and get them in quick. In fact, I'd get them in quick now so that people can vote them up. If you enjoy this evening and want to make a donation, please press the button or click on the button at the bottom of the page. Every little helps to keep us going, and I'm hoping that we will see a few more donations. Tonight, I'm pleased to say we have a colleague and a long-time member and fellow of the BIS, Duncan Lunan, to talk about incoming asteroids and ask the question, what can we do about it? He's already written the book, but I'm hoping he will tell us what we should and will do in the case it actually happens. As his bio says, Duncan is a science writer, specialising in astronomy, spaceflight, and science fiction. He's published some 10 books to date, and this is just one of them. But he has many strings to his bow, having managed space education projects in Glasgow, during which time he built the first astronomically aligned stone circle for 3,000 years. I'm hoping he's going to tell us a little bit more about that. He was also the curator at the Airdrie Public Observatory for 18 years and is a past president of the Astronomers of the Future Club in his hometown of Troon. I'll let him explain how this book came about and how his talk followed on from that. But before I hand over to him, I should say that I've known Duncan for many years and first met him in the bar at the BROP conference. That's the British Rocketry Oral History conferences at Charterhouse back in, I think it was the early 2000s, Duncan, wasn't it?
2000 was my first one, yes.
Was the first one, yeah. And
first one I went to, yeah.
Yeah, and he and your colleagues from Astra. Now, let me get this right. The association in Scotland to research into astronautics, isn't it?
That's right.
Good. So we'll hope you're going to tell us more about that as well, because I think you were talking more about the Scottish history of rocketry in those days, and I certainly remember you mentioning that you were taken out to the Hebrides to see a rocket. Or something about a very young man at the time. And I'm hoping that we'll go the full whack and we'll get spaceports in Scotland and Skyroar off the ground to make it all happen. So you can tell us a little bit about your trip to the Hebrides as well. And I'm going to hand over to you, and the floor is yours then. Over to you, Duncan.
Thank you, Alistair. Yes, it's all true. I've been a full-time writer since 1970, and specialising in astronomy, spaceflight, and science fiction, as Alistair says. I was for most of my adult life involved in Astra, which started its days as the Scottish branch of the BIS and became independent in 1963. Just at the point when I went up to university, and I played a major part in getting it established after the Scottish branch had folded. The bit about the rocket range is also true. I went out to South Uist on spec when I was 13, having saved up my pocket money over the previous winter in hopes to get out there and see a missile launch. And due to what in retrospect was probably a case of mistaken identity, I got shown just about everything before they realised I wasn't the son of a high-ranking RAF officer, which I had never claimed to be. It was all a mistake on their part. But I got to see the lot, including the launch of a Firestone Corporal at 400 yards, which I can tell you, having seen all three, is more impressive than a Saturn one at 3.5 miles or the shuttle at 5 miles. It was an overwhelming experience. The Astronomy Project, the late Professor Archie Roy, who was in his day chair of the BIS Scottish branch, was invited to head up this project, and he passed it on to me. He said, "I think I know someone who's crazy enough to do it," and those were his exact words. The brief was to build an astronomical monument in modern materials under the Jobs Creation Scheme, and I persuaded them that it couldn't be, they wanted a working monument, so it couldn't be a copy of an ancient site. I would have to find the site, design something according to the ancient principles. And once that was agreed to, I said, let's get rid of the modern materials and build it in stone as a tribute to Archie Roy and other experts connected with the city. That too was agreed to, and then I did what I did. The picture on the screen, if you've got it, should show me, quote, outstanding in my field, in the original stone circle, which was built by Royal Navy Helicopter in 1979 when I was project manager. In 2016, it was removed to make way for redevelopment of the area. But thanks to a public campaign, I was commissioned to find a new site on the east end of the old park, as it turned out, and redesign the circle to fit it. So that too has been done. It was re-erected in 2018, 40 years to the day after the helicopter operation. And it is not yet open to the public, but we hope it will be possibly in the early part of next year. So that, I think, touches on all the points Alistair asked me to mention. And we can move on to the subject. I renewed my BIS membership earlier this year, and I was sitting in on one of the talks a couple of months ago when Alistair said he'd like to have a speaker on asteroids. So having written a book about how to protect Earth from asteroids, I volunteered. This is the book. It was published by Springer in 2013. It's the result of what in Astra, I should add Astra no longer exists, but in its day we had what we called discussion projects, where we would select a topic, we would brainstorm it, we'd set up a schedule of meetings in which members or guest speakers would cover some aspect of the subject, which would be followed by group discussions, and we'd talk through that aspect and hopefully come to some conclusions and move on to the next. Now, this particular one was proposed by a former president of Astra called Bill Ramsay, who played a major part in all of my non-fiction books one way and another. He has just finished a stint as president of the Educational Institute of Scotland, which is no mean feat to have accomplished and pulled off. He's now the past president of that. At the point where he proposed this particular project, we had just affiliated to SpaceGuard UK, and we'd had a couple of major public meetings in Glasgow with Jay Tate of SpaceGuard UK, the SpaceGuard Observatory in Powys. And it led Bill to suggest we do a discussion project on the theme, if we knew there was going to be an impact in 10 years' time, what could we do? And out of the available options, what would we do? And looking at it, looking at the issues, the thing about it was he had chosen 10 years, not to be too soon, so that nothing could be done, but by comparison with the 7 years it put to put humans on the moon after Kennedy's declaration I believe this nation should commit itself. There was time to get something major done, and obviously this, in a situation like that, if we knew it was going to happen, the stops would be pulled out and big things would be done. I'm going to compare this with two exercises which have been held by NASA recently. I want to compare and contrast, if you will. The first one was held 2 years ago. The discussion group in question were given this, presented with this diagram, that there could be an impact 8 years from the imagined time of the scenario. And initially, there was a considerable uncertainty as to whether it was going to hit, but if it was going to hit in April of 2027. And they took their 8 years over several days of discussion in the simulation, and eventually concluded that this thing was going to hit Denver, and they sent a probe, an imagination, to it, which established that it had a dumbbell shape, and what its characteristics were. And then on approach, they sent a missile with a nuclear warhead in the attempt to deflect it. And in the way of simulations, which are obviously under the control of the moderator, what happened instead of deflecting it was that they shattered it, and the biggest piece was now on collision course with New York. Nothing more could be done, and they lost New York, and that was that. And a lot of people said, given 8 years' notice, is that really the best we could do? And I'm going to suggest that probably a great deal more could be accomplished. In the second exercise, which has just taken place, they gave the group only 6 months, from April of this year to October of this year, before they would get hit. Again, there was still considerable uncertainty as to whether the object would hit the Earth. On day 2, they were told that it would hit the Earth, but there was still great uncertainty as to where it would hit. It could be anywhere between the Pacific, the Atlantic, or the old world. And that generally the group found that they were floundering. They didn't know what, if anything, they could do in the time. And at the point where, given the spread of possible impact points, they really had a great deal of difficulty working out what they were supposed to do with it. It got narrowed down until this became the possible impact area, at which point they were told it was too late anyway because there were only a couple of months left. And it narrowed down still further into this area between Slovenia and Germany. And this was going to be the impact area in close-up with the radius of the possible consequences. And then still nothing could be done. And they finally, as it gave the discussion group a break and said, "Oh, it's not as big as we thought it was. It's only going to take out this area," and with a radius of total destruction about 200 kilometers across. Major destruction, 200 kilometers across. And at that point, they decided they would abandon the simulation and talk about what they'd learned so far, and that was the end of that one. Quite what of use has been learned out of these exercises, I'm not sure. The results of this most recent one haven't been published, as far as I know. So we are going to talk about the thing on a considerably greater level, I hope, of practicality. We are in the early chapters of the book, which were under the heading, "Is There a Danger?" We went through the possible hazards from comets and the results of cometary impacts to date. And we went through the same exercise in chapter 2 with asteroids. And I'm going to assume that everybody watching this is familiar with the nature of the danger and the differences between comets and asteroids. We decided that we had to pick what we came to calling Goldilocks, an object which was not too easy to dispose of and not too hard, not in an impossible orbit to reach, nor yet too easy, and we eliminated comets. We looked at all the comets that had been studied to date, and no two of them were alike. And we concluded that between the difficulty of reaching most of their orbits, and particularly the most hazardous ones, and the uncertainty of what we'd find when we got there, we would simply drop asteroids and drop comets and focus on asteroids. So we're going to be talking clearly in this case about what originally was a main belt asteroid coming from between the orbit of Mars and the orbit of Jupiter. And I have to shrink that again in order to move on. So down it goes. And out of those, the ones that have been perturbed from the asteroid belt past the orbit of Mars are divided into various different categories. And we need to be talking about one which is either in the Amor class or the Apollo class, which will actually be crossing the orbit of the Earth. And looking at the typical orbits of the Apollo asteroids, they look too difficult to reach at the present level of technology. So we're looking for something in the Amor class. And under advice from J. Tate and David Asher of Armagh Observatory, we came down to the idea of an object in an orbit similar to Encke's comet, in that it would give us several chances in 10 years to intercept it, with an orbital period of approximately 3.3 years. But the aphelion still would be out well beyond the orbit of Mars. The perihelion would have to be much nearer to the orbit of the Earth to make it practicable to reach it. With a look at the orbital dynamics, it proved possible to do this. In fact, David Asher had found an object of similar characteristics with a study group he was working with in Japan. They had found an object called 2011 AG5, which was in quite a similar orbit. Composition currently unknown, fairly small, but a potentially hazardous asteroid. Its next pass will be in 2040, which is quite a long way, which will be quite a long way away from us. So it is not an immediate hazard itself, but something of that nature is what we decided we would focus on. And J. Tate discussed the composition of likely objects with us, from which we concluded that a nickel-iron asteroid would probably be very destructive if it hit, but also very difficult to deflect. And we came down on a chondritic asteroid, not a carbonaceous chondrite, which would probably be too fragile and would be easily shattered, but a single homogeneous body, roughly spherical, a kilometer in diameter, of a type that corresponds to many meteorites that fall on the Earth. So that had defined what Goldilocks was. Now, you could say, and some people did at this point, you're just playing international rescue here. The thing about Thunderbirds was that the mission they had to do was always calculated to be within the capacity of their spaceships. And that is fair comment. But on the other hand, there was no point in setting ourselves an impossible task like that last NASA discussion group. We wanted to end with a positive result at the end of the 10-year period, so that we could demonstrate things that could be done and get results. So, looking at what a 1 kilometer carbonaceous, a 1 kilometer chondritic asteroid would be likely to do, it would be comparable to the impact in Northern Europe that formed the Nordlingen-Rees feature, and that hit something like 14.5 million years ago. It was considerably bigger than ours, but it created this very large impact ring. It was actually a double asteroid. The city sits within a part of it today, and the debris field extends all the way over to Moldova. It would have been a very destructive event in its time. I had actually written for the artist Sidney Jordan, who was running a comic strip in the Daily Record, a description in a storyline of the impact of a similar object in the Pacific off Easter Island. And Sidney had illustrated that, giving you a fair idea of its destructive results, with punching a crater through the seafloor into the magma, into which a Venus explorer, which happened to be on test off the island at the time, got sucked, and they had considerable difficulty getting it out again. He mentioned the waves being formed round the impact event, but he didn't do much depiction of them. Chesley Bonestell famously did this cover for an article by J.E. Eniver back in the 60s, which pointed out a lot of the consequences of big impacts. You'd have a plasma column above the impact site, volcanoes going off wherever they could all round about it due to the ground shock, and a huge inward circulation of air and water, initially with tremendously destructive effects, including the waves, which could easily be of this kind of size if the object had hit the ocean. So a very serious threat. There's Jay Tate with Lord Rees at the Space Guard Observatory. And as I said, Jay gave us a lot of very useful advice at this stage of the project. There's Space Guard. And he said, the object, if this happens in the present day, is most likely to be detected by the Pan-STARRS telescope on Hawaii. And it would be reported to the Minor Planetary Center in Cambridge, Massachusetts, initially. And in order to know that it's going to be, that it's going to hit, and roughly where it's going to hit, you're going to need to have its orbit charted by radar as it goes past, either by the Goldstone antenna in the Deep Space Tracking Network, or by Arecibo, which was still upstanding at the time, or possibly by this new asteroid detecting radar, which NASA then had under test with the inspiring title of Kaboom, because it operates in the Ka band. They got very good results with this, but it hasn't been deployed yet, as far as I know. So Jay said, in order to have time to set up those radar observations, which you are going to need, the object will be detected initially, optically, probably by the Pan-STARRS telescope. It'll pass the Earth on the outside, away from the sun. And with the radar observations, you'll end up with a diagram like this, which will give you an error ellipse showing at its closest approach to Earth that it's going to be somewhere within this volume. And with more accurate study, more accurate still, and ultimately what you hope is going to happen is that the Earth will be outside the final ellipse. If it's not, you've got trouble. And Jay reckoned that when the chances of impact got down to on the order of 25%, the alarm bells would be ringing, big things would be done. But if the final ellipse was even smaller and you were actually within the diameter of the Earth, then a full-scale flap would ensue. Now, to look at the likely results of this, we consulted Lembit Opik, who was then an MP and had organised the parliamentary debate on asteroids held in the House of Commons not long before. And he asked for his assessment of what was likely to happen. Said what will happen is that there initially will be a big hostile public reaction to the fact that no preparation has been made, given that this was a known hazard and had to happen sometime. And in response to that, governments are likely to throw together a program and give the scientists and engineers involved a blank check. Money will be absolutely no object. Spend what needs to be spent and make this thing go away. And the governments in question will then focus on maintaining civil order, because they'll have a great many problems to deal with. Not least that if we know in what area of the world it's going to fall, there's going to be economic collapse, big movements of population, massive civil disruption. They'll have quite enough to contend with on that front. They'll just let the scientists get on with it and try to save the world. That was his analysis of what would happen. And we reviewed what technology was available and what possible answers there might be. We didn't favour what Jay Tate calls the Bruce Willis option, which is try to blow it to bits. And we looked at possible gentler solutions, such as the one posited by this chap, Ivan Yurkovsky, and promoted by Ernst Opik as a likely answer to such problems, which he was concerned with even back in his day. What Yurkovsky reckoned was that by altering the albedo of an object orbiting the sun and posing a threat, you could actually change its orbit. Given sufficient time, that might work in effect. That you could paint a pattern, carefully worked out pattern on the object, and the differential effect of sunlight reflecting off it would alter the orbit sufficiently to miss, given enough time. But you are probably talking decades rather than a 10-year slot, which is all we've got to play with. There's also the idea of the gravity deflector, where you take a massive spacecraft under continuous thrust from plasma jets, and as the asteroid, low though its gravity is, tries to pull the tractor towards it, the spacecraft keeps thrusting away, and in effect it tows the asteroid behind it. A 4-ton spacecraft, it was reckoned, could deflect an asteroid on this order of size we were talking about, given a period of 20 years, which is longer than we got. So we shelved that one meantime, and we looked at still other options. There's another view of the gravity tractor, which shows you how the beams have to be angled not to hit the asteroid, otherwise you negate the whole tractor effect. But with that configuration, it can be done if you've got enough time. Coming back to that later. There's a diagram of the thrust vectors involved. Now, we looked at our possible options, and interestingly at this point we were working in parallel with a study group at Strathclyde University headed by Professor Max Vasili, whom you will see in a minute. The chap on screen right now is the late John Braithwaite. He was second in command on the Stone Circle project, having trained with Charles Frank and Avimo, become an expert in both optics and electronics. And he was a member of a group under Dr. Peter Waddell at Strathclyde University, who solved the problem of the flexible mirror, which was known until that time as the Loch Ness monster of optics. Flexible parabolic mirror, which would remain parabolic and producing a tightly focused image, even as you change the shape of it. In this instance, by withdrawing air with a vacuum pump from behind the flexible sheet. It works. I attended a couple of very dramatic demonstrations in the 1980s, and at one point was actually, when I was in Houston, asked to go to a private meeting with a senior officer in what's now the US Space Corps to brief him on it. Right. Now, friend of mine at Glasgow School of Art, Gordon Ross, member of the Industrial Design Unit there, allied John's ideas to his own concept of a parabolic solar sail called Solaris, which he'd already been working on. And he came up with this quite complicated design. It's a tertiary mirror system. The tertiary mirror is the one that's flexible and the focus can be adjusted. So you could position it upsun of the object you wanted to deflect, and the energy being collected by the very large parabolic mirror, much larger than this, it's not to scale, would be focused by this mirror onto a hotspot on the asteroid or comet. Notice that in this situation, it's in balance. The pressure, light sail pressure generated in that direction by the focus beam exactly counters the pressure of the sunlight initially falling on the main mirror. We shared this work with Max Vasili's group, initially at Glasgow University and then at Strathclyde. And they decided that this arrangement was too elaborate and too vulnerable to fail. They still felt that either solar deflection or mass drivers were the two best options to deflect an asteroid. And they came up with a concept they called mirror bees. Since this slide's come up next, I'll briefly mention this was John Braithwaite's concept of how the flexible mirror would work in space by having a transparent membrane over the actual reflecting surface and varying the internal pressure so that you could alter the focus. This is Max Vasili with part of the experimental test rig which he set up at Strathclyde. And this was the concept that he came up with, which he called mirror bees. Simplifying the design, he would preferably send a fleet of parabolic mirrors to create a hotspot on the surface of the asteroid, create a jet, and move it. He was then told by the optics department at Glasgow University that they could, because the sun is not a point source, he couldn't get a sufficient focus without positioning the mirrors so far away that they would have to be implausibly large, which was one of the reasons why he also went on to study mass drivers. We felt ourselves that in taking away the focusing mechanism, they had created a problem for themselves, because now they were being told they couldn't focus it. And we were a little bit irritated by that. At this point, I tried to discuss the matter with Rusty Schweikart, who, through the B612 Foundation, is taking a great interest in the problem of protecting Earth from asteroids, and came to Glasgow with the Institute of Space Explorers. And he wouldn't listen to me. He literally just stood there and laughed in my face. He said the idea of sunlight deflection has been totally discredited. The plume from the asteroid will destroy your collector within minutes, and the whole thing is a nonsense, and I won't listen. And he just went on laughing until I went away. So I went back to Max with that, and he said, yes, I know the paper he's talking about. It was written by two Chinese physicists. He said, it's very interesting, but they've made huge assumptions. And one of the assumptions is that the shape of the plume will be similar to that of a rocket exhaust in air. And consequently, there'll be a wide spread of particles around it, so that wherever you position the collector, it'll be covered by them and destroyed by them. He said they've also assumed that the particles will be large enough to do damage to the mirror, and that they will cling to it, that they'll stick to it. And he said none of these things are guaranteed. So he set up a series of experiments at Strathclyde, testing to see whether a mirror off-axis from the plume would or would not be contaminated or destroyed by it. Would the plume be of this shape, like the Nerva nuclear rocket tests in the 60s? Or would it be much more diffuse, like the Nerva plume itself would have been in space? So he set up experiments, which initially he performed in a nitrogen atmosphere and then repeated in vacuum. And he discovered, interestingly enough, that in fact the plume would be narrow. There'd be a broad spread round it, but it wouldn't be of large amounts of material. And the further off beam you were, the less accumulation there would be on the mirror. And furthermore, it didn't cling. A very light vibration was enough to shake it off again. So he said, no, this damage hazard has been vastly overrated here. So Gordon Ross and John Braithwaite then came up with a number of designs aligning their concepts to Max Vasily's, and using the mirror to power a laser instead of actually concentrating on a hot spot on the asteroid. And as I said, they came up with several different methods of working this, still with John's transparent surface, which he argued could be made self-repairing if any particles did penetrate it, and could definitely, simply by varying the pressure, shake off any particles that clung to it, and could be replaced if it turned out they were destroyed fairly rapidly. You could carry multiple spares and just put another one over the mirror. And in 2012, we held a seminar in the Bridie Library at Glasgow University Union, to which Gordon brought a demonstrator. He's got a little parabolic mirror there, and a thin slit open in the curtains behind him. And even through that thin slit, the laser, which was on the back of the mirror, powered by the collector here, was creating a hotspot which was large enough that it would have ignited paper if you'd kept it stationary, which is not something you want to do in a library. So he kept it moving as he was demonstrating it, and turned it off fairly rapidly after he'd made his point. But that was where they got to. These things could be launched, folded up, like the reflectors of the TDRS satellites, and that's one being launched from the Challenger in 1983, and deployed in space. They look like that. They are compact enough and probably low enough in mass as well that you could launch large numbers of them with rockets such as Falcon 9 and definitely Falcon Heavy in time to intercept the asteroid when it next comes round the sun 3 years after the first encounter. So we, in theory, we'd got the answer. But the one worrying thing was what kind of regolith would the asteroid have? That's Gaspra, photographed by the Galileo probe. And that's the ultraviolet image of it, as I recall, looking through the regolith at the more heavily cratered surface below. The thing that remains uncertain with mirror deflection or laser deflection is, are you actually going to transmit that thrust into the body of the asteroid, or are you just going to move the regolith around? Which led us on to the next concept. As I said, both we and the Strathclyde group had concluded that the other major option was mass drivers. And Max Vasily had been using the results of a concept called Madman that had been developed in the States. The idea this group had was that they would deploy automated mass drivers on the surface of the threatening asteroid. They'd drill into the rock, they'd bag the samples in electrically conducting material and fire them up these spikes to produce essentially a rock jet, and to deflect the asteroid that way. And their paper demonstrated that this was at least feasible in theory. And we looked at the numbers with respect to our asteroid, and we took the worst possible case in which, due to combinations of its rotation and composition, it would prove to be necessary to deflect it right across the visible diameter of the Earth, and at right angles to its line of flight. That's the least favourable deflection option. But we went for that, and we discovered that for a carbonaceous asteroid, a kilometre in diameter, you would need to apply a thrust which was a very small fraction of a space shuttle main engines, and actually came to 0.04% of the thrust of a wartime V2. But you're going for a rendezvous, in this case, 6.6 years after discovery and 3.3 years before impact. You've got to maintain that thrust for the whole of that time, and in order to achieve that worst case for deflection. And it, again, might not work. Reaching it, we realized the requirements were in energy terms, very similar to those for a Mars flyby, which had been proposed as a precursor to a Mars landing in the post-Apollo program. And our mission, we concluded, required, well, when we looked at the orbital diagrams, we realized if we could reach the asteroid on a home in orbit for the first encounter with the solar reflectors, the second time would definitely not be reachable on a home in orbit. A more advanced propulsion system would be needed. And to quote General Tom Stafford, "We know NERVA works. In the time available, we could get it up and flying." And so we were going to do a manned mission to the asteroid using NERVA propulsion and boosters, and launching with the Space Launch System, and comparing all of this with previous studies. That would be the expanded version of the SLS that would be used, the Block 2 version. We would need a minimum of 31 of them. The pacing element here, as Max Vasili pointed out to us, had to be the storage of liquid hydrogen in space as you're assembling your fleet. He reckoned 3 months was the very best that could be achieved, and that was assuming advances on today's technology. The vehicle assembly building is not going to be able to handle more than 4 at a time, and the availability of launch pads is also going to be a crucial factor. I'll skip past that because time is moving on. These are just pictures of studies that have been done on possible manned missions to asteroids. The thing is that at the moment, we've only got one launch pad for the Space Launch System. And if we're going to want to get, it turned out to be a minimum of 31 launches within a 3-month period to assemble our fleet, you're going to need more launch pads. You're going to have to open up the ones that weren't developed for the Apollo program, and quite possibly take the one back off Elon Musk that he's using at the moment, if you're doing it all with the SLS, which is what we were assuming at the time that this project took place. Whether Elon Musk could do it all for us is another matter, which we can consider later. That wasn't in the book because it hadn't happened yet. But one thing we did look at and were impressed by was this idea of capturing a small asteroid in a big net. The net could be very useful. That, incidentally, that's design that's been produced for electromagnetic radiation shielding of ships on long duration missions. It's so massive, it would take an extra SLS launch to put its unit up. So we need a better answer than that. And the one that we came up with was that we would cluster the ships round an inflatable module of the Bigelow type. We've missed a slide somewhere. I don't know where it's gone, but let me run back. Right. There should be another one before that somewhere. Yeah, there's this one showing working on the surface of the asteroid. The net would be very useful for working in such low gravity. It's about 1,000th of a G. And we discovered that a single solar collector of the type that at this point have supposedly been tried and not proven effective, but could still generate enough power to run all the mass drivers, which means you can take their individual nuclear reactors off them, much to the relief of the guys working on them. We reckoned they would need specialist crews like the Space Shuttle main engines did, and they'd be temperamental. You couldn't do this in automation, not in so short a time scale at any rate. Somewhere here, there should be a diagram of the ship, and I don't know why I'm not picking it up, but you can see them there. You'd cluster the 12 ships round that inflatable core and deploy the mass drivers onto the surface. And this was the final configuration we came up with. It turns out that even for that worst deflection case that we had postulated, the 12 nervous ships of our fleet would have 3/4 of the mass necessary to achieve the gravity tractor deflection in 3.3 years. And assuming any more favorable case for the deflection than that, probably that alone would do it. Obviously, they'll still try the mass drivers, but if they don't work, and again, the problem is the regolith. Studies in microgravity have shown that what probably would happen with the asteroid regolith is that you'd create rock tsunamis, which would, whenever you fired one mass driver, an outward tide of regolith would push the others off axis and quite possibly go right around the asteroid, come back and smash the first one. So that's the big weakness of that scenario. But gravity tractor may very well be able to do it. We reckoned that we would have a rotating hub suspended by a tether in the direction of the asteroid, and cabins on a boom, which would allow to counter to some extent at least the effects of microgravity. And the asteroid, which remember would be 1 kilometre across, so it would actually be this size, would provide them with nearly 50% of shielding from solar and cosmic radiation, which ought to make it tolerable to the astronauts on a 4-year mission. So, as I said, the regolith is your remaining problem that may knock, especially if it's a pebble field like Bennu or Itokawa. Right, suppose even that does not work for whatever reason, and the weak point is in keeping those plasma jets firing for 3.3 years. If it doesn't work, what Limit OPIC told us was when your 10 years is nearly up, it's coming straight at the Earth, desperate measures will then be tried. This was the point where we brought in nuclear deflection for the first time, and Nigel Holloway and David Asher advised us on that. It, in theory, might work, but the risk of shattering the asteroid and creating, as Jay Tate said, turning a cannonball into a shotgun blast, that risk is very great. But it would be tried. And the obvious thing, rather than have a free-for-all, which Rusty Schweikart feared would happen with different nations firing their own weapons and trying to push the thing in different directions away from themselves, the obvious thing is for the task force to take those nuclear charges with them and detonate them precisely where needed under control, with the ships now standing off. The next option, brought to our attention by Colin McInnes, is impact deflection. And here, what he intended to do was send a big mass on the order, as I recall, of 80 tons over the poles of the sun by solar sail so that it would hit the asteroid in the opposite direction, coming at it on a retrograde orbit, and so move it aside if it didn't shatter it. Now, I think it was Ivan Dale of the Mars Society came up with a point that you wouldn't necessarily have to shift all the way over the poles of the sun. An oblique impact with the asteroid would probably suffice. But we then came to the idea of using a mass driver to fire smaller projectiles, but have a controlled series of impacts, again directed by the task force ships standing off from the asteroid. This one, illustrated here by Sidney Jordan and Theon Rich, was the one which was included in a couple of papers John Braithwaite and I published in JBIS back in 1983 for nuclear waste disposal in space. And we had some very interesting ideas as to what could be done in the aftermath of that if it succeeded. Andy Nimmo of the Space Settlers Society then asked, could the same energy being used to power the mass driver be used to power a sufficiently powerful laser to deflect the asteroid? Obviously, in theory, yes, because the amount of energy collected by the mass driver is by definition equal to the amount of energy required to deflect the asteroid, and it could be directed. And we discovered there was a US study called D-STAR, which had proposed to do exactly that, and they kindly let us quote their figures. So that too, obviously, would be tried. And there have D-STAR and other groups in the States have conducted their own studies with rock samples, firing laser beams at them, and found results very similar to Max Vasilis. So, yeah, all possible. What you would be looking at this late stage would be what's called the red line, where you're moving the impact point across the surface of the Earth and hopefully off it. And J. Tate made a very important point here, and it concerns the film Deep Impact. He didn't quite put it this way, but the question is, why is Deep Impact called Deep Impact? The fragment that comes in and hits the Earth strikes the sea obliquely. And in the posters, there are a few things missing. There's virtually no ejecta from the impact. You do see the blast wave spreading out, but that presumably dissipates before it reaches land. You never see it again. And Jay said, if you're dealing with an object a kilometre across and you can point it and in the right place, there are regions where the seafloor is more than five kilometres deep, and you wouldn't penetrate the crust. You wouldn't even penetrate the seafloor. You would get the initial blast wave and the water wave, but the other destructive effects would be minimized. And in fact, there is such a region off the west coast of the United States. It's a fairly small target, but conceivably, if you couldn't deflect the asteroid away from the Earth, you could hit that. And so the consequences would be much reduced. You'd still have the waves to contend with, but there you go. A great deal of water would be injected into the atmosphere. And I've been able to find very little in the way of studies of what happens to it afterwards. This is obviously a diagram out of one, but it came with no caption and no reference. However, you're certainly going to have very big storms. You're going to have possibly a global blackout for up to 2 years due to dissolved solids from the water and the water itself. An effect in the upper atmosphere akin to noctilucent clouds, but Fred Hoyle thought even from the airburst of a large asteroid, that could be sufficient to trigger another ice age. Perhaps not quite as sudden as that, but on the other hand, maybe. The results from the Chelyabinsk airburst are not encouraging in this respect. After a year, the dust had still not settled. It was just going round and round the world. And with the Shoemaker-Levy impacts on Jupiter, there are still high concentrations of water vapor in the atmosphere over the impact sites, which again is not encouraging. However, and the effect would be, at least for a couple of years, akin to nuclear winter. And when we held our seminar at Space Garden Powys in 2004, one of the contributors was Arthur Hodkins of the Sphere Environmental Consultants, whom I had met at Charterhouse at the Broke conferences. And he had said, I want to come to this. I have a major contribution to make. And indeed he did. He started off by talking about cometary impacts and saying you'd need Star Trek technology to deflect those. You're going to need matter transmitters and tractor beams and all kinds of things. Andy Nimmo and I begged him not to start with this, but he insisted and nearly lost his audience. But then came a very dramatic moment. Behind him on the wall, there was a poster showing at monthly intervals the aftermath of a big impact. And it ended up after 6 months. The pictures looked as if they'd been taken from the cold and the dark, in fact. They looked familiar. But the last one was captioned 6 months after impact, 90% of the human race is dead. And Arthur said, I'm going to show you how to reverse that percentage. And it turned out he was an expert on shelters and stockpiling. And he said, if you've got 10 years notice, you can build shelters. Some nations that are not nuclear powers, like Sweden and Switzerland, already have them for large numbers of people. If you increase your production of coal and oil by 20%, you can produce enough supplies to keep those shelters powered. You can grow crops underground. And in fact, although this picture is of Iron Mountain in the States, the Scottish branch of the Mars Society visited an identical looking site on Loch Fyne under Bencruachan, where deep inside the mountain in the hydroelectric scheme, in the turbine hall, they've got simulated daylight and have been doing experimental programs of growing plants for years. It could be done, said Arthur. It would take a massive reorganizing of resources, but given 10 years notice, with sufficient stockpiling, nobody has to die. And Lembit Opic's reply to that was, governments won't do it. They'll be so busy maintaining martial law and generally trying to keep the lid on civil disorder, they will not put the public to the extra hardship of a rationing program lasting 10 years, even although it would ensure their survival at the end of it. And Bill Ramsay said, that's just one politician's opinion. I choose to disregard it. And so you pays your money and you take your choice there. But it could be done with 10 years notice. On Earth, massive measures could be taken. So moving on, and I'm aware of my time running out, so I am going to run through the last bit very quickly, which is a look at, suppose on the other hand we succeed. What can we do with all this lovely technology that we're left with? And we discussed Colin McInnes's ideas of harvesting asteroids, bringing them in through the L2 point to the Earth-Moon L2 point, and harnessing, making use of their resources from there. Jay Tate said he wished to register strong objections to any proposal to deliberately bring an asteroid near the Earth. So, but it could be done. That's one of the options. Or the old 1950s idea of hollowing out asteroids and turning them into spaceships. In those days, they thought ion drive was the only possible propulsion, but we've moved on from that. Colin Cox, in the book Islands in Space, suggested hollowed out asteroids the whole asteroid interior hollowed out, which was apparently the inspiration for Arthur C. Clarke's Rendezvous with Rama. And we've still got the mass driver. And as I said before, that was part of the Project Starseed idea John Braithwaite and I had. What we were going to do was build O'Neill-type construction shacks out of the tanks of the heavy lift boosters. We were using one proposed by Bob Parkinson for the purpose, so they'd be going up in pairs. They could be added stably to the structure. And the Starseed could then be moved out to the L2 point, could build solar power satellites out there instead of at L4 and 5, as O'Neill suggested, brought down to synchronous orbit on 2-to-1 resonance paths. And putting this together with Eugene Matloff's ideas of putting Daedalus engines onto O'Neill habitats, what you could do would be to move O'Neill habitats, which would be fully shielded, into the close vicinity of Jupiter to extract deuterium and helium-3 as the Daedalus project proposed. And once you've done that, to quote Jerry Webb, within the solar system, Daedalus is pure Flash Gordon in its potential. You can open up the whole lot. There's a wave rider in the atmosphere of Jupiter as a precursor of a flying factory. There it is, the factory, to collect deuterium and helium-3. You could be out in the Oort cloud in a couple of 100 years, or at least filling the Kuiper belt with habitats. And it's interesting that Gavin Roberts painted that in 1979, before the Kuiper belt had officially been discovered. And from there, you can go to the stars. You can take Daedalus habitats, Daedalus engines on O'Neill habitats. You can go to the stars. You can go to planetary systems with gas giants and zero-G resources. Epsilon Eridani looks particularly inviting. You've got the alternative approach, which David Hardy has very kindly painted for me here, which was suggested by Freeman Dyson, of growing trees on comets and greening the galaxy. I'm thinking of doing another book on that. That painting has inspired me. And in 30 million years, the two waves of expansion meet on the far side of the Milky Way. They meet as aliens because they've evolved differently on the way around. And once we've sorted out the problems that generates, we can decide what we're going to do next. So to close, asteroids are nature's way of asking, how's that space program coming along? And that is the viewpoint we're taking here. So there we have it. The book is still in print. I regret to say Springer's have published it at textbook prices, and for some reason, even the Kindle book is pretty expensive, but it's in print. There's lots more in it. This has been a rush job on its contents, but thank you very much for listening. And if there are questions and discussion, I shall look forward to that. So,
well, thank you very much. I hope you can hear me there, Duncan.
I can.
Fascinating. Great. And really, I probably could have let you have another 5 or 10 minutes. So if you wanted to carry on, but we have some questions coming in, and I'm sure we've got a load more coming. I think my first question, though, is which comes first, climate change causing complete disruption to the planet, or your asteroid?
Well, this came up in discussion between John Braithwaite and me all the way back in the winter of 68, 69, when I formulated my thesis of the politics of survival, which I've used as a framework for the book. It's starting to look a bit dated now in some respects, but the idea of underlying it was how to use space technology to ensure the long-term survival of mankind and thereby of terrestrial life in all its forms. And at that time, we thought that we'd have to spread out to a distance of 10 light years to ensure that we were safe from supernova shockwaves and the like. But with O'Neill habitats, you can put that much closer. Even if we encountered a totally destructive hostile extraterrestrial intelligence, which I don't believe will happen, but if it did, if we had O'Neill habitats spread through the the Kuiper belt and into the Oort cloud. I don't think they'd ever get us all. So I think we'd have met that objective. Now, when John and I were thrashing it out, he started arguing with me quite early on, saying we've got to produce terrestrial solutions for terrestrial problems first. And at one point, he angrily said to me, how can you possibly suggest that dealing with impact threats should take priority over, for instance, solving hunger worldwide? And I said, well, put it this way, if something a mile across has just hit the Pacific Ocean, we are not going to finish this cup of coffee sitting here, because the effects will be global and fatal. And I would regard that as pretty damned immediate. So, yeah, the thing is, we are in a situation right now where there doesn't appear to be an impact threat directly for the next century or so, barring an incoming comet, which we probably couldn't deflect anyway. So we are not in immediate danger. And we are, meanwhile, developing the capabilities that would allow us to deal with something like this if it did come up. So it's reckoned we've now discovered something like between 95 and 98% of the objects over a kilometre in diameter currently crossing the Earth's orbit. There will be lots of smaller stuff. NASA's going for the eventual detection of all the objects of 100 meters and above. But the big threats, it looks as if we've been very, very lucky. There's nothing coming our way at the moment. And in the time in which there could be, when the potentially hazardous asteroids become more potentially hazardous, and the comet Swift-Tuttle is the one to be really scared of, because that could be an extinction event. And it's got 2 very close passes in the next 300 years. But yeah, we've got time to continue to develop the capabilities and be able to meet this if it happens. And we have been incredibly lucky in that regard. And I've closed the book with the imagined editorial in the Times at the end of the Professor Challenger novel by Conan Doyle, in the Poison Belt, where the Earth does encounter a comet, which, for the purposes of the novel, is diffuse and simply spreads through the atmosphere and makes everybody pass out for 24 hours. And the effects are fairly drastic, but they're not. It's not an extinction level event. And Conan Doyle imagines the editorial that will appear in the Times the following day or a couple of days later. And I ended the book with that because it preaches the message. It says, if you've been very lucky, tact tent, as we say up here, learn from it and don't stick your neck out again.
I suppose the question is, as long as we don't distract people from the current problem of climate change, if the asteroid isn't going to be around for 300 years, I think we've got climate change to sort out before then.
Don't think I'm of the group that says, okay, the climate is changing, but it's not as bad as that. Having written Children from the Sky, I did a lot of research on the climate changes of the last few thousand years. And we are nowhere near the level, for instance, of the medieval warming, when they were growing vines all the way up into Scotland. Greenland was green when the Vikings reached it, which is why it's called that. And this was the epoch of the very severe droughts on the west coast of America. The Northern Hemisphere was a lot warmer then than it is now. At the same time, the Southern Hemisphere was a lot warmer. The parts of the Antarctic coast were ice-free, and there were huge colonies of elephant seals whose remains have now been discovered. And this all coincides with the most active period of solar activity since the Bronze Age, which was also very warm in the Northern Hemisphere. So what we're facing at the moment is not that dangerous. Yeah, we need to take steps. We should look after our environment. But we've only 10 years to save the Earth. The first time I heard that was in 1960. And too much scare tactics don't improve the situation.
That was the fuel crisis. I remember it well. I was trying to build aeroplanes at the time. Now, we do have some questions coming in here. And coming to the top is one from Steve Salmon, who says, if the target asteroid was tumbling or spinning, would it still be possible to create a hotspot using a laser or similar beam?
Well, Gordon reckoned that in that situation, what you'd create was a trench with a jet coming out of the trench at wherever the beam then happened to be impinging. And he thought that would actually be helpful as regards focusing the jet and minimizing the danger that fragments and plasma would hit the collector. He designed, in fact, an alternative version of the Solaris, which he called Archimedes, which involved 4 elliptical mirrors tethered, shining onto the asteroid all at the same spot. And the trench would simply migrate around the surface of the asteroid as it rotated or tumbled. If you're doing it by mass driver, in that situation, what you're going to need is to spread them all over the surface of the asteroid. But you might, on the other hand, be lucky and be able to concentrate them all at the one spot and fire them all continually in the one direction. There are very wide range of possibilities here. The one thing that really is not affected by any of these considerations is the gravity tractor. And so what we think we've demonstrated is that of the 12 Nerva ships, if the mass drivers themselves had a quarter of the mass, each one had a quarter of the mass of the ship that took it out there, they would have you could put the mass drivers back on the ships, and you would have sufficient mass to deflect the Goldilocks asteroid, even in the worst possible case. So this is certainly within the range of the doable. We don't have to throw up our hands and say it can't be stopped. We're helpless. We're very far from helpless.
Okay, right. We've got another one here that seems to have been voted up. Well, I'll go in the order we've got them at the moment. This next one is from Trevor Bennett, and he says, if an asteroid were to get through and destroy mankind, would there be enough time that its energy, that the energy in the sun for some other life form or force to emerge from the seas and make, dare I say it, better fists of it?
Well, there's a fascinating book written quite a long while ago by a chap called Dougal Dixon called After Man, in which he supposes that there is a catastrophe which takes us out and the rest of the higher life forms with us. And so he looks at the world 60 million years later, comparable to the period after the Chicxulub impact, and tries to guess what life forms would survive and would evolve to fill the ecological niche. So that penguins, for example, have turned into whales, and the most dangerous predators are flightless bats, and elephants have evolved into mammoths, and there isn't anybody around like us. And maybe the flightless bats are the best chance because they're bipedal and they've now got hands and arms. But on the whole, the world is getting on perfectly well without us in his model of the future. I would like to think that it is still our job to protect Gaia from asteroids. So we need to improve the fist we're making of it. I've reprinted the whole of the Politics of Survival as an appendix to Incoming Asteroid. As I say, it's looking slightly dated now because I formulated it in 1969, but it's still been the core of virtually all of my published work since. So
you're going to do a rewrite at some point?
Yeah, I might do. I've got a lot of other things I'm getting on with at the moment. I see somebody said there, lots of other talks I could give. You've seen nothing yet, pal. I've only been back since January.
Right. Well, we better get back to some of these questions, because we've got one here from John Davies, who's up in Edinburgh, as we know. We know that many NEOs are rubble piles. How does their lack of cohesion affect these defection strategies?
Again, the gravity attractor is the one that will work regardless. But probably if you hit one of those with a sufficiently powerful nuke, it would just scatter, and the fragments would not be big enough to do great harm. All the way back in 1971, I wrote a story which started off as an essay, and the working title remained with the story. It was called How to Blow Up an Asteroid. It was published in Galaxy. Very heavily rewritten, but I have since got it into print in a book of my own, the way I wanted it to be. And all the way back then, I was thinking, along the same lines as J. about turning the cannonball into a shotgun blast. What happens at the end of the story is that the threatening asteroid is blown apart, and the astronauts up in space are congratulating themselves on having saved the world at the point when the big fragments start hitting, and that's the end of the story. But that is not going to happen with a rubble pile, as far as we know. You will just blow it into pebbles, and at best you might get a very spectacular meteor shower. We should be all right with those. We felt that we were aware of the rubble pile concept, and we decided that it was too easy. This could be a bit like that competition back in the early years of the century about communicating with other planets. Mars was excluded from the prize on the grounds that it was too easy. But it might be in that category. But this was why we decided on a homogeneous lump of rock, which, as JT said, I didn't mention this, but it would had to have been originally a part of the crust of something much bigger.
Yeah. Right. Well, we better move on then. We've got a few more coming in. Dean Sherman is saying, so if I understand correctly, the more time we would have in discovering an asteroid on trajectory with Earth, the more time we have to deflect it? ?
Yes, assuming that governments get their act together. The reason Bill Ramsay picked his 10 years timescale was so that governments couldn't leave it to their successors, and so that there would be serious public alarm that would force governments to act. If you tell them it's going to happen in 50 years' time, they'll say, oh, well, it's not my problem. I won't be here then.
Well, most governments don't survive more than 5 years these days. The working part of government.
Exactly.
So maybe we ought to reduce it to 5 years, not 10.
Yes. Well, that's too short, I think.
Right.
There is that famous exchange between Jerry Purnell and the deputy director of NASA, where the deputy director said to him, if we started now, we couldn't put a man back on the moon within 10 years. And Purnell said, expletive, 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 it only took you 7 years last time. But that's probably the sort of timescale in which we want to have a crash program like this.
Yeah.
5 years, it'll be too short. We'll kill people.
Yeah. Okay. Right. We've got another one. Fabrizio Bernardini is saying how the recent missions to asteroids changed this and other scenarios for deflecting an asteroid.
I think we've covered that, really. The big surprise is that both Bennu and Itokawa turned out to be rubble piles, though we still don't know what lies beneath. But we hadn't seen anything like that before, and suddenly it looks as if they may be common, which is perhaps relatively good news. But I'm not so sure. I see that a study has just been published suggesting that the Chicxulub impactor was a carbonaceous chondrite. And carbonaceous chondrites normally break up in the atmosphere, but several miles or kilometers across probably wouldn't have time to. So I suppose this is conceivable. But on the whole, I would say the recent discoveries haven't changed it all that much.
Right. Well, in fact, Fabrizio's corrected this one by the look of it. He says, hey, the corrector made a mess of my question. I was talking about warmings and anthropic effect.
I don't get that one.
I think this was going back to his question, which was about what asteroids we've actually been and visited. We've learnt a little bit about the fact that they're warming them up, and the anthropic effect may be slightly different to what we originally thought. We'll have to get Fabrizio to ask that question or clarify that question a bit more.
Yes, I don't get that one.
No. Okay, we'll move on. Right, we've got this one from Alex Wood, who says, apart from Lembit Opic, are you aware of any politicians in the UK or elsewhere with a particular interest in NEOs?
No, in a word. When Lembit was talking about the immediate reactions to the discovery, if it was made, he said, the lonely furrow that I plough in politics today will be gone. He was speaking as an MP then, and he's not even got that now. No. And as far as I know, not much. And the UK government did bring out a report of a study group on the NEO hazard, which J. Tate quoted at Charterhouse, you may remember. And he said how remarkable it was that not only that the British government had brought this out, but that nobody laughed. And other parts of the world, in fact, particularly France, had said, what an improvement. This is much better than the sort of rubbish we normally expect from the UK. But in fact, of the 14 recommendations they made, the only one that was implemented was to set up a UK space centre for asteroids. And instead of giving it to Jay, they gave it to Lester, who apparently did nothing with it. So that responsibility has now been turned over to J. Tate, except that he hasn't been given the funding that Lester had. Mm. So also, in the last chapter of the book, which we haven't mentioned at all, Professor Richard Crowther gave us a lot of inside briefing on the studies at the United Nations, or under the auspices of the United Nations, that he had been conducting, ending with proposals that were ratified by the General Assembly just before the book came out, to set up international warning networks and to look much more seriously at what would be needed to protect the Earth in the circumstances. And from what I can gather, I gave a version of this presentation to the Clydesdale Astronomy Society a few months back, and Arthur Harris was one of the people who came in on the discussion, and he said, nothing's been done since. The programs that were set up have run their course and finished, and at the moment nothing's happening. And that's the best information that I have in reply to that question. At the moment, nothing's happening, except that NASA has been given the funding to complete the brief it was given in 1992 to find all the hazardous objects over 100 meters in diameter. And they're going to be launching a satellite in about 7 years' time, which will complete the survey of near-Earth objects begun by the NEOWISE application. So we will at least know our enemy that much better.
Yes, know they exist. Right. Well, actually, Fabrizio's clarified this. This this is probably the question that he was actually asking before he changed the order of them. The point is not that we didn't have similar global warming or not, is the reason why we have it now. And the fact that the anthropic impact may make things worse. Working with geophysicists, I assure they all know the past history of the Earth.
Not all of them. As the result, the notorious hockey stick graph that dominated this debate until comparatively recently took no account whatever of the medieval warming, or the Roman warming, or the Bronze Age warming, or the intervening mini ice ages. It just showed an even rise in temperature corresponding to human industrial activity, and it wasn't valid. I say I'm not a total I'm far from being a total skeptic. I accept, for instance, that the carbon dioxide count is rising steadily. And if it's not showing in the warming effect yet, we should be scared in case something major suddenly kicks in. Yeah, we should not be messing with the planet. I just don't believe that we've actually only got 10 years to save the world yet again. That's alarmist and not helpful in my view.
Well, I've got solar panels on my roof, and all my water's hot water from solar arrays as well. Right. Well, we've got the final. Yeah. Oh, I've had them 10 years now. Right. We've got the final question here from Robert Law.
Yeah. Hi, Robert.
Should we have a satellite in space to monitor the asteroids and comets? I think you may have answered that one.
Yeah, there are several up there doing it at the moment as a sideline, and the various companies who want to go and use the resources of the asteroids, they're intending to launch satellites for this purpose, and I included illustrations of several of them in the book. They haven't happened. They were supposed to have happened by now, but they haven't. There was a question which, as far as I know, has not come up, but I got advance notification from Jerry Nordley, who said he would try to be sitting in on this, but he sent me advance notice of his question, which was, should we if private companies come in on this and save the world, should they be given the resources of those asteroids as a reward? Yeah, I hadn't thought of that one, but among the many things in the book we haven't had time to talk about, there was a quite fascinating meeting that I set up where we had some people who were very strong on we must get rid of the United Nations treaties thing, and very strongly in favour of retaining the United Nations treaties and finding workable formulae from them, which various writers like Bonnie Cooper, for instance, have pointed out is entirely possible. But we had these guys banging on, for instance, about nobody can make money out of anything unless they own it, so we've got to get rid of the clause that says you can't. So I brought along Professor, I'll get my tongue around his name in a minute, Professor Angus McAllister from what is now the University of the West of Scotland, who is an expert particularly on the Scottish law of leases. He also writes science fiction, and I keep pointing out that his science fiction publisher ought to be drawing attention to the fact that he's a best-selling author because he has written the only guidebook to the Scottish law of leases. This is a set text for Scottish law students. So he sold an awful lot of copies of that. But the thing is, as he pointed out at that meeting, it is entirely possible to make money out of property that you don't actually own. And until the recent abolition of fee duty, technically nobody in Scotland owned anything. The Scots have a bit of a reputation for making money out of it. But as regards internationally, the law of leases regarding mineral resources is a very highly developed area of law, way beyond his area of expertise. But he said we could get experts on it if you wanted. But it is entirely possible for a nation or a corporation to lease a piece of land to exploit its mineral rights, although it's located in another country. It happens all the time. So creating a suitable regime to exploit the asteroids under the at least the 1967 United Nations Treaty, perfectly possible. Bonnie Cooper and colleagues wrote a book about the resources of the moon, in which they suggested setting up a lunar equivalent of the New York Port Authority, which they thought would work very well in that context. Again, these are things that can be done with effort. The big question, which of course we didn't discuss at all, is where do people like Musk entering the picture affect it? I think Jerry Nordley's question is much the point in that regard, because the Falcon 9 had only just become operational when this project was going strong. And look where they are now. Yeah, you wouldn't possibly need a fleet of 12 Nerva ships if you could do it with Musk's starships and a bit of extra boost.
And if he's willing to pay for it, let's go for it. We'll do it commercially.
Yes, well, he is thinking of reaching Mars with those ships.
Mm-hmm.
And as I pointed out, if you can reach Mars, you've got the delta V you need to reach an Earth-crossing asteroid.
Yeah.
And in fact, you don't need the fuel to break into Mars orbit or descend to the surface or come back up from the surface. At one point, we were calling our Nerva fleet, and it's one of the reasons why we had 12 ships, was so that we could use figures from Das Mars project, because it's Werner von Braun's Das Mars project without the gliders.
Yeah. Right. We've got actually Fabrizio responded here, and he says fair enough to that last question. So
good.
We've got that one, but he's asking me another one on the side. Right. Steve Salmon asks a slightly flippant question, but the inspiration for the mass driver engines on a target asteroid, was it taken from the UK Hammer film Moon 02 in 1969?
It hadn't occurred to me. The curious thing about Moon 02 is that none of the rockets have tanks. But one of the things they definitely did get right was that you can't see rocket exhausts in vacuum. Somebody pointed that out. It might have been somebody from the BIS back around 1955, criticizing the Jeff Hawkes strip in the Daily Express because Sydney always drew visible exhaust for his rockets. But apart from the fact there's no tankage on any of the rockets, Moon 02 wasn't half bad. They did go that bit too far with the all black sky, because there's a bit where the characters come up out of a mine shaft on the far side of the moon in the middle of the night, and they still can't see any stars. But yes, I enjoyed Moon 02. It was one of the better spin-offs, I think, from 2001.
Okay, we've got another question here, which is from Jerry Stone. Well, you know Jerry well.
I do indeed.
Right. He says or asks, would there be much in the way of Would there be much in the way of resources to give companies that save the Earth if the asteroids have been deflected or shattered?
Well, you probably wouldn't go back to that one, because if we've hit it with everything that we've talked about tonight, before we manage to deflect it, it's got big glassy trenches dug through its regolith. It's got radioactive patches where the nukes were closest to. It's been hit by a damn great powerful laser beam from D-Star, and probably Colin McInnes's impactors as well. It'll be in a pretty parlous state. That one probably not, but maybe we can come to some kind of a deal. And the thing is still out there, and maybe it's still got the mass drivers attached to it, so they could, if there was anything valuable, they could drill in and extract it and fire it back to Earth. It's still possible.
So the answer is to mine them first, which will change the balance of the whole thing, and that may be enough to deflect it.
Well, you could go further than that. Back in the 70s, when Astra ran its discussion project, which led to my books New Worlds for Old and Man on the Planets, the only thing we could think of at that time to deal with hazardous asteroids was to send out a task force and dismantle them, make things out of them and ship them back to Earth and let the rest disperse as dust. So maybe we're coming back to that idea.
Yes, could be. Right, a final question here from Bob Morris. He says that ESA has approved the Comet Interceptor mission. Shouldn't there be an NEO interceptor mission?
Well, there is the Didymus impactor, which we're involved in. NASA's sending the main body, and we're sending the observing probe. So we are involved.
Yeah. So it is happening, and by we you mean ESA?
Yes.
Right. Yes. Yeah. Well, that was fascinating. I think we've got a few comments in the chat here, but I'll probably leave them till another time. I think we lost a few of our audience right at the beginning. They missed out on the start of your talk, so I'm sorry about that. But we'll try and see if there's a problem our end, but we guess that it's probably more of their problem than ours. But thank you very much for a fascinating talk. It really is interesting to hear back in history so long ago that you were doing these talks that we'd almost forgotten that these had been discussed way back in the 70s, 80s, and 90s. And we're now bringing them back to life again. So I think we've got to thank you for keeping the ball rolling on that one.
Right.
So thank you
for having me.
Well, thank you very much for an excellent talk. And I hope the next time we get you along, we'll actually be able to do it from the BIS, because we'll get you down and we can have a good beers afterwards.
That'd be nice.
Afterwards. We haven't had any of those for a long while now.
No, indeed. Let us know if you're up here, Minta.
Well, yeah, I was thinking of going, but when they locked me down for the third time, I thought, well, I'll hang on for a little bit longer. But yes, I must also thank Elizabeth for once again coordinating the evening behind the scenes. I think it worked well for me anyhow, and it seemed your presentation worked well as well. Thank you, Duncan. Now, if you've enjoyed tonight's talk, and this is talking to the audience again, and want to make a donation, please remember to click on the donate button. As I said earlier, everything helps to cover our costs. Now, we've got some events coming up. On the 15th of September, we've got Dave Shaler, who's going to tell us what our Space Chronicle magazine is about and how important it is to examine the rich resources of the Society archives and to capture the special moments in space history in print. And then next comes World Space Week from the 4th to the 10th of October. The theme this year is celebrating women in space. So if you're running any event at that time, please let us know or go in through the World Space Week website, because we are the BIS is the UK coordinator of all events to do with the World Space Week. I'm still hoping to get a speaker for Wednesday, the 6th of October, which will, I hope, cover the very subject of women in space. And finally, on the 21st of October, we hope to have our very first return to the BIS for a live lecture. We've got Pete Swan dropping in on us on his way from the USA to the IAC in Dubai. And he'll be bringing us up to date with the development of the space elevator. So we're looking forward to that, and we're hoping it will be our first live meeting at the BIS on the 21st of October. There's a lot more to come, and we're hoping that we'll all keep you involved in what we're going to try and do on the 28th of October, which is to celebrate the 50th anniversary of Prospero and Black Arrow. We're bringing out special editions of our Space Chronicle for that, and we'll also, I hope, have a few articles in Spaceflight. But I'm hoping to run a full day event on the 28th of October. I think it'll be virtual because a lot of people want to do it from various sites. So I'm hoping to get that all together in the next couple of months. So I better stop now and let you all get away for supper. Thank you again, Duncan, for an excellent talk, and thanks to the audience for participating. See you next time. Bye-bye.